Welcome back. 11 episodes of integration are behind us. Today, the course pivots. We've been computing the integral of f of x dx continuous sums of infinitesimal pieces. Now we shift to the sum from n equals 1 to infinity of a sub n, discrete sums of countably many pieces. Same spirit, very different questions. With integrals, the central question was usually, what's the antiderivative? With infinite sums, the central question is, does this even converge? Some infinite sums add up to a finite number, some blow up, some oscillate. The behavior depends on how fast the terms shrink, and there are surprises. Today we lay the foundation. We'll define sequences and series rigorously. We'll meet three families that every calculus student must know cold: the geometric series, the harmonic series, and the p-series. We'll prove the divergence test. And we'll close with Euler's Basel problem from 1735, one of the most surprising sums in all of mathematics. Let's go. First definition, sequence. A sequence is just an ordered, infinite list of numbers, a sub 1, a sub 2, a sub 3, and so on forever. Formally, it's a function from the positive integers to the real numbers. You feed in n, you get out a sub n. 3 examples to keep in mind. A sub n equals 1 over n gives the list 1, 1/2, 1/3, 1/4, and so on, shrinking towards 0. A sub n equals negative 1 to the n gives -1, 1, -1, 1, bouncing back and forth. And a sub n equals n over n plus 1 gives 1/2, 2/3, 3/4, 4/5, climbing toward 1. Now the key concept, convergence. A sequence converges to a limit L if its terms eventually get and stay arbitrarily close to L. Formally, for every tolerance epsilon greater than 0 you specify, there is some cutoff n such that all terms past the nth lie within epsilon of L. This is the same epsilon n definition from real analysis, just applied to a discrete index. The three examples, 1 over n approaches 0. Negative 1 to the n does not converge. It has no limit, it just bounces. N over n plus 1 approaches 1. If a sequence has no limit, we say it diverges. Sequences are the building blocks. Series are made of them. Now, the central object of this whole half of the course, the series. Given a sequence a sub n, the series, the sum from n equals 1 to infinity of a sub n, is the formal expression a sub 1 plus a sub 2 plus a sub 3, and so on, where the dots mean and so on forever. As written, this is just a symbol. It doesn't automatically mean a number. We have to define what it means. Here's the definition. Build the sequence of partial sums. S sub 1 equals a sub 1, S sub 2 equals a sub 1 plus a sub 2, S sub 3 equals a sub 1 plus a sub 2 plus a sub 3. In general, S sub n is the sum of the first n terms. Each S sub n is a finite sum, a number, no infinity in sight. Now ask, does this sequence of partial sums converge? If S sub n approaches S as n approaches infinity, we say the series converges to S and we write the sum of a sub n equals S. If the partial sums don't converge, if they blow up, or oscillate, or anything other than settling down to a limit, the series diverges. So a series is really just a special sequence, the sequence of its own partial sums. The infinite sum symbol, the sum from n equals 1 to infinity of a sub n, is shorthand for the limit as n approaches infinity of S sub n. That limit is what we are really computing whenever we talk about an infinite sum. Three families illustrate the whole spectrum: geometric, harmonic, p-series. Let's meet them. First family. The geometric series. A geometric series has the form: the sum from n equals 0 to infinity of r to the n equals 1 plus r squared plus r cubed, and so on, where each term is the previous one multiplied by a fixed ratio r. This is the most fundamental series in all of mathematics. It's the model everyone else gets compared to. The beautiful thing about a geometric series is that we can compute the partial sum in closed form. Take S sub n equals 1 plus r squared, and so on, up to r to the n minus 1. Multiply both sides by r times S sub n equals r plus r squared, and so on, up to r to the n. Subtract S sub n minus r S sub n equals 1 minus r to the n. Factor S sub n times the quantity 1 minus r equals 1 minus r to the n. Solve S sub n equals the quantity 1 minus r to the n over 1 minus r. 3 lines of algebra, no calculus required. Now take the limit as n approaches infinity. If the absolute value of r is less than 1, then r to the n approaches 0. Raising a number smaller than 1 in absolute value to higher and higher powers drives it to 0. So S sub n approaches 1 over 1 minus r. That's our boxed formula. The sum of the geometric series from n equals 0 to infinity is 1 over 1 minus r, provided the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, the terms r to the n don't shrink to 0. They either stay the same size or grow. The partial sums can't possibly converge. The series diverges. Memorize this. The geometric series is your first and most important convergence series, and the formula 1 over 1 minus r will show up constantly. Here's the geometric series made visible. I've drawn rectangles laid end to end along a horizontal axis starting at 0. The first rectangle has width 1. The second has width r, where I picked r equals 0.6 for the picture. The third has width r squared, which is 0.36. The fourth, r cubed. Each new rectangle is r times the previous one. The ratio stays constant. Where does the chain end? At 1 over 1 minus r, the dashed gray line on the right, with r equals 0.6, that is 1 over 0.4, which is 2.5. The rectangles get smaller and smaller, and although they never quite touch the dashed line, they fill in the entire length up to it in a limit. That is the geometric series, geometrically. Each partial sum reaches a little further to the right. The total reach as n approaches infinity is exactly 1 over 1 minus r, and this picture also makes the failure case obvious. If r were greater than or equal to 1, the rectangles wouldn't shrink. They'd stay the same size or grow. The chain would extend to infinity, and the series would diverge. The shrinking only works when the absolute value of r is less than 1. First worked example. The cleanest infinite sum in mathematics. The sum from n equals 1 to infinity of 1 over 2 to the n equals 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. Each term is half the previous, so it's a geometric series with first term a equals 1/2 and ratio r equals 1/2. The formula. For a geometric series whose first term is a and whose common ratio is r, with the absolute value of r less than 1, the sum is a over 1 minus r, plug in, a equals 1/2, r equals 1/2, so the sum is 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is 1. The whole infinite sum equals 1. Exactly. Not approximately. Not in the limit of approximation. Exactly. This is the resolution of Zeno's paradox, 25 centuries old. To walk from one end of a room to the other, you first walk half the distance, then half the remaining distance, then half of what's left, and so on. Infinitely many steps. Zeno concluded motion was impossible. But the steps shrink fast enough that they add up to a finite total. 1/2 plus 1/4 plus 1/8 and so on equals 1. The whole room. You walk infinitely many subdistances in finite time because their sum is finite. The paradox dissolves once you have convergent series. Archimedes essentially knew this. He summed geometric series to compute areas under parabolas around 250 BC, but a clean theory had to wait until calculus. Second example, a divergent geometric series to remind us what failure looks like. The sum from n equals 0 to infinity of -1 to the n equals 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. Geometric, ratio r equals -1, but the absolute value of r equals 1, not less than 1. So the geometric series formula doesn't apply, and we should expect divergence. Look at the partial sums directly. S sub 0 equals 1. S sub 1 equals 1 minus 1, which is 0. S sub 2 equals 1 minus 1 plus 1, which is 1. S sub 3 equals 0. S sub 4 equals 1. They alternate forever between 0 and 1. There is no single limit. The sequence of partial sums does not converge. By definition, the series diverges. Easier diagnostic, the terms themselves don't go to 0. -1 to the n stays at size 1 forever, just flipping sign. If your terms don't shrink, your partial sums can't possibly settle down. That's the divergence test, coming next. And aside for the curious, there are exotic summation methods, Cesaro sums, Abel sums, in which 1 minus 1 plus 1 minus 1, and so on is assigned the value 1/2 by averaging the partial sums. These are useful in some advanced contexts. But in this course, the sum of a sub n always means the limit of ordinary partial sums, and by that standard, this series diverges. Don't be tricked. Now the most useful diagnostic in elementary series theory, the divergence test, also called the nth term test. Theorem. If the sum from n equals 1 to infinity of a sub n converges, then the terms a sub n go to 0. The logic is straightforward. Convergence means the partial sums s sub n approach some limit s. The shift by 1, s sub n minus 1, also approaches s. It's the same sequence, just relabeled. The difference a sub n equals s sub n minus s sub n minus 1 approaches s minus s, which is 0, so a sub n approaches 0. Done. The contrapositive is what we actually use. If the terms do not go to 0, the series diverges. That's the divergence test. Easy to apply, just compute the limit of a sub n. If it's non-zero or doesn't exist, you're done. Divergent. Example. The sum of -1 to the n has terms that don't approach 0, they bounce. Divergent. Done. Example. The sum of n over n plus 1 has terms approaching 1, not 0. Divergent. Done. The test is fast. Now the critical warning, because students mess this up constantly. The converse of the theorem is false. A sub n approaching 0 does not imply the sum of a sub n converges. The terms going to 0 is a necessary condition for convergence, but it is not sufficient. The next example is the canonical counterexample, and it will haunt you for the rest of the course. The harmonic series. The single most important example in this whole half of the course. The harmonic series. The sum from n equals 1 to infinity of 1 over n equals 1 plus 1/2 plus 1/3 plus 1/4 and so on. The terms 1 over n go to 0, so the divergence test doesn't apply. We can't conclude anything from it. But the claim is the harmonic series diverges anyway. The partial sums grow without bound even though the terms shrink. The proof goes back to Nicola Resme in the 1350s, 300 years before Newton. Group the terms cleverly. The first group is just 1, which is at least 1/2. The second group is 1/2, equal to 1/2. The third group is 1/3 plus 1/4. Both terms are at least 1/4, so the sum is at least 2 times 1/4, which is 1/2. The fourth group is 1/5 plus 1/6 plus 1/7 plus 1/8. All four terms are at least 1/8, so the sum is at least 4 times 1/8, which is 1/2. The next group has 8 terms, all at least 1 over 16, so it sums to at least 8 times 1 over 16, which is 1/2, and so on. Every doubling block adds at least 1/2 to the partial sums. There are infinitely many blocks. The partial sums therefore exceed 1/2 plus 1/2 plus 1/2, and so on, which is infinite. So S sub n approaches infinity. The harmonic series diverges. Slow divergence though. The partial sum S sub n grows like the natural log of n. To reach S sub n equals 10, you need about 12,367 terms. To reach S sub n equals 100, you need about e to the 100, which is about 10 to the 43rd terms, more than the number of atoms on Earth. Slow, but relentless. The harmonic sum will eventually surpass any number, no matter how large. Why is the harmonic series the great cautionary example? Because it shows that terms shrink to 0 is not enough to guarantee a convergent series. The terms have to shrink fast enough. The geometric ratio r to the n shrinks exponentially fast. Enough. The harmonic terms 1 over n shrink only polynomially, not fast enough. That is the entire game of series convergence, how fast do the terms shrink. Third family, generalizing the harmonic series. The p-series. A p-series is the sum from n equals 1 to infinity of 1 over n to the p for some real exponent p. When p equals 1, this is the harmonic series. When p equals 2, it's the sum of 1 over n squared equals 1 plus 1, 4th plus 1/9 plus 1/16, and so on. When p equals 1/2, it's the sum of 1 over the square root of n. The boxed convergence rule. The sum of 1 over n to the p converges if and only if p is greater than 1. Strict inequality. So p equals 0.99 diverges, p equals 1 diverges, the harmonic series, p equals 1.01 converges, just barely, p equals 2 converges cleanly, p equals 3, 4, 5 all converge faster. The threshold is exactly the borderline rate of decay. Terms of size 1 over n don't shrink fast enough for convergence. Terms of size 1 over n to the 1 plus epsilon for any positive epsilon do. The harmonic series sits exactly on the dividing line and falls to the wrong side. Why p equals 1? Because if you compute the integral from 1 to infinity of 1 over x to the p dx, it converges if and only if p is greater than 1. The improper integral test connects the sum to the integral, and the same threshold applies to both. We saw this in episode 8 on improper integrals. The integral from 1 to infinity of 1 over x to the p dx converges precisely when p is greater than 1. Next episode, we'll prove this connection rigorously via the integral test, and as a corollary, recover the p-series rule. For now, memorize the cutoff. P greater than 1 converges, p less than or equal to 1 diverges. That is the most used single fact in series convergence. Closing example, and one of the most famous results in all of analysis. The Basel problem. The series is the sum from n equals 1 to infinity of 1 over n squared equals 1 plus 1/4 plus 1/9 plus 1/16, and so on. This is a p-series with p equals 2, which is greater than 1, so it converges. That much we know from the convergence rule. The much harder question, what value does it converge to? Italian mathematicians in Basel had been computing it numerically since the 1640s. They knew it was about 1.6449. But where does that strange number come from? What is it algebraically? The problem stumped mathematicians for 90 years. The Bernoullis tried. Leibniz tried. They could compute the partial sums but couldn't find a closed form. In 1735, Leonhard Euler, then 28 years old, found the answer. The sum equals pi squared over 6. Pi squared over 6 is about 9.8696 over 6, about 1.6449. Yes, that mysterious number from the partial sums is pi squared over 6, the same pi from circles, out of nowhere. Euler's original argument was a brilliant heuristic. He treated sin x as an infinite polynomial, factored it by its roots pi, 2 pi, 3 pi, and so on, compared coefficients with its Taylor series, and read off the value. The argument wasn't fully rigorous. You have to justify treating sin x as a polynomial, but it produced the right answer. Modern proofs use Fourier series or contour integrals to make the same identification airtight. We won't prove it in this episode. It deserves its own treatment, perhaps later in the series. For now, we just record the result as a marker for how strange and beautiful infinite sums can be. The reciprocals of perfect squares add up to pi squared over 6. You can't make that up. Infinite sums have a long and distinguished history. Quick tour. 5th century BC, Zeno of Elea. His paradoxes, Achilles never catches the tortoise, the arrow never reaches the target, all hinge on the idea that infinitely many positive intervals can't add to a finite total. Zeno took this as a proof that motion is illusory. We now read his paradoxes as the first conceptual challenge that infinite series posed to human thought. 250 BC, Archimedes. Computing the area under a parabolic arc, he summed the geometric series 1 plus 1/4 plus 1 over 16 and so on, which equals 4/3. He didn't use modern notation, but his argument is the first mathematically rigorous handling of a convergent infinite sum. 1400, Kerala, India, Madhava of Sangamagrama discovered that pi over 4 equals 1 minus 1, fort plus 1/5 minus 1/7, and so on, the alternating series for arctangent at 1. The Kerala school had a substantial calculus, flavored mathematics 3 centuries before Newton. The same series was rediscovered by Leibniz around 1674 and now usually carries his name. The 1350s, Nicole Oresme proved the harmonic series diverges by the doubling argument we saw earlier. Stunning result for the time. Galaxies of medieval mathematicians had been working with infinite sums heuristically. Oresme gave the first negative result. 1735, Euler solves the Basel problem. The sum of 1 over n squared equals pi squared over 6. This single result essentially founded modern series analysis as a serious subject. The 1820s, Cauchy gives the modern epsilon n definitions of sequence and series convergence and proves the tests. Comparison, ratio, root, in the form we'll meet next episode. Long, deep history. 2,500 years from Zeno to Cauchy. We're now standing on all of it. Vocabulary recap. 8 items, the whole episode in shorthand. Sequence, ordered list of numbers. Converges to L if the terms eventually stay arbitrarily close to L series. Formal infinite sum, the sum of a sub n, defined as the limit of the partial sums. Partial sum S sub n equals the sum of the first n terms. The series converges if and only if the sequence S sub n converges. Geometric series, the sum of r to the n equals 1 over 1 minus r when the absolute value of r is less than 1, diverges otherwise. The cleanest convergent family. Harmonic series, the sum of 1 over n diverges, even though 1 over n approaches 0. The famous cautionary example. P series, the sum of 1 over n to the p converges precisely when p is greater than 1. The threshold rule you must memorize. Divergence test, if the terms don't go to 0, the series diverges. Necessary, not sufficient. Convergence requires terms going to 0 plus they shrink fast enough. Basel problem. Euler 1735. The sum of 1 over n squared equals pi squared over 6. Just a beautiful landmark. These 8 items are the foundation. Next episode we build the toolkit for deciding convergence. 5 pitfalls. 1. The most important misconception. If a sub n approaches 0, the series converges. False. The harmonic series is the lifelong counterexample. Going to 0 is necessary. Going to 0 fast enough is what's sufficient. We'll quantify fast enough next episode. 2. Sequence versus series. A sequence is just the list of individual terms a sub n. A series is the sum of those terms. They are different objects. A sequence a sub n approaching 0 does not imply the series, the sum of a sub n, converges, again, harmonic. Conversely, if the sum of a sub n converges, then necessarily a sub n approaches 0, but the sequence and series convergence questions are distinct. Always know what you're asking about. 3. The geometric series formula depends on where you start the index. The sum from n equals 0 to infinity of r to the n starts at r to the 0, which is 1, and equals 1 over 1 minus r. The sum from n equals 1 to infinity of r to the n starts at r, and equals r over 1 minus r. Same common ratio, different first term. Check the starting index when you apply the formula. Or, more reliably, identify the first term a and the ratio r and use the sum from n equals 0 to infinity of a times r to the n equals a over 1 minus r. 4. The p-series threshold is p equals 1 excluded from convergence, p greater than 1 converges, p equals 1 diverges, p less than 1 diverges. Strict inequality. The most common mistake is including p equals 1 in the convergent range, but that's exactly the harmonic series, which diverges. 5. The divergence test is one-directional. It can prove a series diverges when terms don't go to 0. It can never prove a series converges. If you find a sub n approaching 0, you've learned nothing from the divergence test alone. The series might converge or might not. You need a different tool. We build those next episode. Recap. Sequence, ordered list of numbers converging if its terms approach a limit L series, the sum from n equals 1 to infinity of a sub n, defined as the limit of the partial sums s sub n equals a sub 1 plus, and so on, plus a sub n. Geometric series, the sum from n equals 0 to infinity of r to the n equals 1 over 1 minus r when the absolute value of r is less than 1, diverges otherwise. The model example, with closed form partial sum from a 3-line algebra trick. Harmonic series, the sum of 1 over n diverges even though 1 over n approaches 0. Proof by Orsme via doubling blocks that each add at least 1/2. P-series, the sum of 1 over n to the p converges if and only if p is greater than 1. The harmonic series is the boundary case and falls just on the wrong side. The threshold will be justified by the integral test next episode. Divergence test. If a sub n does not approach 0, then the sum of a sub n diverges. The converse is false. Going to 0 is necessary, but not sufficient for convergence. Basel problem. The sum from n equals 1 to infinity of 1 over n squared equals pi squared over 6, proved by Euler in 1735. A landmark identity. The pivot is complete. We've moved from continuous integration to discrete summation. The Riemann template stays in spirit, add up infinitely many pieces. But the indices are integers, the starting questions are convergence questions, and the toolkit changes. Next episode, convergence tests. Comparison test, ratio test, root test, integral test, alternating series test. 5 tools to decide convergence for essentially any series you can write down. See you there. That's sequences and series, the foundation. If this helped, hit like, drop a comment, subscribe. It's genuinely the most useful thing you can do for the channel. Post your favorite strange infinite sum in the comments. Special love for the ones that secretly equal something involving pi. Those are the hidden gems, Matava, Euler, Wallace, all hiding in unsuspecting series. Next episode, tests for convergence. Now that we know what a series is, we need a procedure to decide whether one converges. We'll build the full toolkit. Comparison, ratio, root, integral, alternating. 5 tools applicable to almost anything you'll meet. See you there. Sequences and series open the second half of integral calculus. We've spent 11 episodes computing integrals, areas, volumes, arc lengths, surfaces, by chopping continuous regions into infinitesimal pieces and summing in the limit. The summing was hidden inside the integral sign. Now we expose it. Replace int with the sum, replace dx with the step from index n to n plus 1, and you've moved from continuous to discrete. The questions transform. Instead of asking what's the antiderivative, we ask does this infinite sum converge to a finite value, and if so, which value? Some sums add up. Geometric ones do when r are 1. The harmonic series doesn't, even though its terms shrink. The p-series converges if and only if p = 1. These are the first 3 families you must know cold. Next episode, we build the convergence toolkit, comparison test, ratio test, root test, integral test, so that for any series you can write down, you have a procedure to decide whether it converges. Subscribe so you catch it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.